Okay, now, good morning, everyone. Hopefully, my voice is audible and my screen is viewable. I mean, my presentation is viewable. Anyone just reply so that we can start the class. Am I audible and my presentation is visible? Okay, fine. Somebody replied. Thank you very much. No problem. Let us start. Now, in the last class, we have talked about dictionaries. That is nothing but binary search trees or some data structures which has a unique elements or a keys. So that's what binary search trees comes into the category or concept of dictionaries. Now we have seen binary trees in the last class, and we at okay, we were at we have seen insertion, and we were at the deletion part. I mean, now insertion, you know that we will search for the place where the key or the element has to be, or the node has to be inserted, and then it depends upon whether it is the left child or the right child that has to be inserted. So insertion is pretty much easy when compared to deletion. And in insertion, we try to apply the logic of searching for the key or searching for the node, and then insert the node as the left child or the right child. Now in deletion, it's not that easy when we use deletion. Deletion has three possibilities. Now, it can be a leaf node that we are trying to delete. That is what we talked in the last class. And for example, in this case, 15 is the leaf node, 45 is the leaf node, 56 is the leaf node, 70 is the leaf node, 95 is the leaf node. So deleting the leaf node is very simple. Now, what we need to do it is we need to just make the, for example, if we are trying to delete 15, 15 is the right child of node 12. So we simply have to make the reference of the right child as null in node 12. So 15 gets deleted. Now, there is another possibility that a node which we are trying to delete will have one child left or right, or one subtree left or right. Now, for example, if you take node 12, if you're trying to delete node 12, node 12 has a right child. We call this as right subtree. And then if we take node 60, node 60 has got a left child at the root there of the left subtree. So it's the left subtree which node 60 has got. So the second possibility is that deleting a node with one subtree, right or left, or one child right or left. Then the third possibility is to delete a node which has two subtrees, left as well as right. And in this case, for example, if you see node 52 is there, it has both left and the right child, or left and right subtrees. Node 90 is there, it has both left and right subtrees. Node 65 is there. This entire thing with 60 as the root is the left subtree, and this entire thing is the right subtree. As well as node 40, which is a root. Even root has, in this case, has got two subtrees. That is, this from node 12, 15 is one subtree, that is the left subtree, and from 65 till whatever we have as part of its children is the right subtree. So there are three possibilities or three scenarios. Now, deleting, as I told you, deleting a leaf node is very easy. Let us try to look at deleting once a node which has one subtree. Let us consider the case of 12. In 12, node 12 has only one subtree, that is the right subtree with node 15. So what we have to do is, whether it may have other children of node 15 doesn't matter. But what we have to do is the node 12 is what we need to do is node 12 we are deleting. Node 15 is the right subtree, and node 12 is the left subtree of node 40, its parent, left subtree of its parent. So for node 15, the link is, from node 12, node 15's link is deleted, and there is a link from node 40. That is, node 15 is made as the left child of node 40. So this is how a node with one subtree is deleted. Let us look at another scenario. Node 60 is there. Node 60 has got one subtree, and there are so many nodes. There are 3 nodes in the subtree. So in this case, what happens is node 60 is left of 65, and 52 is also left of 60. So we have to make a link, or we have to make node 52 as the left child of node 65. So we first make remove node, then we make the left child of node 65 as node 52, and the entire tree structure remains the same. The rest of the entire tree structure remains the same. So this is how we delete nodes with one subtree, left or right. Now, the most difficult part of scenario is deleting a node with two subtrees, that is left and right subtrees. Let us consider this node 90. Node 90 has got node 70 and node 95. Now here, if you observe, node 70 and 95, they are not, they don't have their children. They are the leaf nodes. So this is one scenario. And this is pretty much straightforward, that when we are deleting a node, for example, node 90, any of these children, two children, should be made as the node itself, and rest of the child remains the same. For example, let us consider 70. So when we are deleting node 90, we can either make 70 as node 90 and delete node 70. So tree structure remains the same. The property of binary says tree satisfied. Or we can make, for node 90, when we are deleting node 90, we can make the right child as the node and delete the right child. So this is one possibility. This is pretty straightforward, because the left and the right child do not have their children. But if you observe, what we try to do it is, how we generalize this is that when a node with two subtrees, left and right, both left and right, is deleted, we will select the largest node from the left subtree. Remember, largest node from left subtree, and replace with the root. Not root. Replace with the node which we are deleting, and then the next node of that tree, we will make it as the left child. We will look at that scenario. Or in left subtree, we are selecting the largest node. If we consider the right scenario, if we are considering right, replacing the right node, then you have to select the smallest node from the right subtree. So that is why here in this case, if I consider replacing with the left part or left subtree, then there is only one node. So this is the this is the largest node itself. So we are replacing it. Or when we consider the right subtree, this is the only node. So it is the smallest node itself, and we are trying to replace it and delete that node. Now let us try to take another scenario. Suppose if we are trying to delete node 65. It has both subtrees. Left subtree starting with the node 60, that's the root. Right subtree with node 90, that's the root of the right subtree. Now, when we are deleting this, node 65, if we consider the right, if we are considering the left subtree to replace that node, then node 60 is the maximum element in the left subtree. That element will get replaced with node 65, that is the node we are deleting. So we replace node 65 with node 60, because we are considering left subtree, so it's the largest element from the left subtree. Then we make the child of the node as the left subtree. So this satisfies the criteria. But suppose if we are considering the right subtree, in the right subtree we have to select the smallest element and replace with the node. So node 70 is the smallest element. We are replacing that with the node which we are deleting. So that gets replaced and simply node 70 gets deleted. The rest of the links are same and the structure of the tree remains the same. So this is how deletion in binary search trees is performed. There are three possibilities, that is deleting a leaf node or deleting a node with left or right subtree and deleting a node with both left and the right subtrees. Deleting the node, leaf node is very easy. Just simply make the left or the right child as null, the parent of the make the left and the right child in the parent node as null. That deletes the leaf node. If you are having two nodes, if you are deleting a node with one subtree left or right, then delete that node, but make the parent, whether it is left or right, as the link to the child of the left, or the child or the root of the left or the right subtree. Then if you have two subtrees, left as well as right, then you can select either the left subtree and choose the largest element or node and replace with the node which we are deleting and subsequently create the links. If we considering the right subtree, then choose the lowest or the smallest element and replace with the node which we are deleting and subsequently attach the links. So this is how, or this was the basics of the binary search trees or dictionaries. Now let us quickly move on to the next topic, that is in this case priority queues. Now priority queues also has keys. They are priority queues are what we call what we say are binary trees, and remember, but they are not binary search trees. So the name queue has come up because the position where we perform a delete operation, that's always at the root. Now let us look at this tree. As I told you, heaps are also binary trees. They are not binary search trees. So that is why you can observe here that 80 is the node, 70 is the right child. So in binary search tree, this property, I mean, the right child should be greater than the node. So this doesn't satisfy. So this is not a binary search tree, remember, but heaps are binary trees and heaps are complete binary trees. So if you look at this, the property, there are two types of heaps, that is max heap and min heap. In max heap, the parent is always greater than its children. In min heap, the parent is smaller than its children. But when we talk about heaps, we consider that andar hai sha. When we talk about heaps, we generally talk about max heaps or maximum heaps, where the parent is greater than its children. So if you look at this binary tree or this heap, I mean, it's okay. Let's for instance say that it's a binary tree. If you look at this binary tree, node 80 is there. Is its children smaller? Yes, 45 and 70. It doesn't matter where these children are. It can be 70, can be this side, 45 can be this side, doesn't matter. So here in this case, when we consider this node 80, both its children are smaller than 80. So at this stage, the property of binary tree is satisfied. Then at this node 45, both the children are lesser than its parent, that is node 45. So at this stage also it is satisfied. Now these nodes 40 and 35 are leaf nodes, so there's no doesn't matter. Whereas node 70, if you look at node 70, node 50 is smaller, so this node satisfies that property, but node 90 is greater. So what we do is, this is not a heap, this is just a binary tree. To make this as a heap, always have to remember that the node should be greater than its children. So in this case, it's node 70, which is the parent, and node 90 is greater than. So this violates this property at this place, 70 and 90. So what we do is, we call something as heapify. We will shift the node so that the heap property is satisfied. So 90 becomes its parent and 70 becomes its child. So at this stage, it is satisfied. This property is satisfied. That is, 90 is there, 50 is less than 90, 70 is less than 90. But at its parent stage, that is 80, 9, and its children is, child is 90, it's not satisfied. So again, we have to replace this with its parent. I mean, swap parent and child. So when we swap parent and child, at every stage or every node, except the leaf nodes, obviously, you can find that the property of a parent greater than the children is satisfied. So this is a heap. Now remember, this property, what we are trying to check over here, is known as relational property. So a heap, in heaps, two properties has to be satisfied. One is the relational property, that is, a node will be greater than its children if it's a max heap. A node will be smaller than its children if it is a min heap. But we only consider max heaps. So every node should be, its children should be smaller than that node. That is known as relational property. The other property is the structural property. So heap has to satisfy both relational and structural. In structural property, what we say is, we say that the heaps are complete binary trees. Complete binary trees, not full. They are complete binary trees. Now, this is an algorithm, simple algorithm for performing insert. Now, what happens is, let us first try to see what insert is, and then we perform adjust and how to perform delete operation. And let us first try to see how to insert. Now consider, insertion is nothing but we are trying to insert elements from a heap. Now here, the heap is empty and 40 is the first element we are trying to insert. Now when we are inserting 40, that will be the root of the binary tree, or the heap itself, root of the heap itself. Now suppose I want to insert node 80. Look at this side, node 80. Now as the next element. So very first thing is, it has to satisfy structural property. So node 80 is not inserted as the right child. It has to satisfy structural property, that is, a heap is a complete binary tree. So obviously, complete binary tree means we have to fill it up level by level and fill the nodes up level by level and within levels from left to right. So node 80 is inserted as the left child. But when node 80 is inserted as the left child of node 40, structural property is satisfied, but it is violating the relational property. So child and parent are swapped. So node 40 becomes child, node 80 becomes the parent. So when node 80 is inserted, it is inserted as the left child, and then to maintain the properties of the heap, the nodes are swapped, and now 80 becomes the parent of 40, or the 80 is the root of the heap. Now suppose if I have to insert node 35. If I have to insert node 35, node 35 will not be inserted as the left child or right child of node 40 over here at this stage. Why? Because it has to maintain the structural property. So always it is inserted as the last element in each level. I mean, depending on from left to right, it is inserted. Actually, not last element, left to right, it is inserted. So node 35 will be inserted as the right child of node 80. When it is inserted as the right child of node 80, it satisfies the structural property. Then we also have to look at whether it satisfies the relational property. That is, a node should be greater than its children. In this case, node 80 is there, and we have children 40 and 35, which are greater, the parent is greater than its children. So this is satisfied. So this is also a heap. Now we will insert another node as 90. So 90 node will be inserted as the left child of node 40, because this level all the nodes are full. So we have to binary, it should be a complete binary tree. So we start inserting as the left child of node 90. Oh, sorry, left child of node 40. So now what happens is node 40 left child structural property is satisfied, but relational property is not. That is, node 40 is smaller than node 90. So node 40 comes here at place of 90, and 90 comes in place of node 40. Then at this level, that is the second level, node 80 is there, which is smaller than node 90. It's not possible. So 90 gets swapped with 80. So ultimately we will have node 90, node 80, and node 40. So this is the 90, 80, and 40. So this the part is the heap. The tree which you see on the right side is the tree after, is the heap after inserting node 90 and adjusting the elements. Then another node 45 I am inserting. So if I insert 45, I will not insert as a left child. I have to insert it as the right child of node 80. Now when 45 inserted, is it satisfying? Yes, it is satisfying both structure as well as the relational property, because node 40 and 45 are smaller than node 80. And 80 and 35 are already satisfied. Then if I insert node 50 now, when I'm inserting node 50, it should be inserted as the left child of node 35. This is this satisfies the structural property, because that is how we are inserting, and then but violates the relational property. So 35 is replaced with 50. So 50 comes here. So this part, the right side, what you see is a heap. 50 and 35 are replaced. Now, do we have to replace 50 with 90? No, because the property is satisfied here. So if you observe, wherever we are inserting from, that is at the leaf level we are inserting, at the last level we are inserting, from there we have to check its parent, then its parent, then its parent, until we reach the root node to adjust the node so that the relational property is satisfied. So now let us look at the algorithm. Now here is the algorithm for insertion. We have an array A. In that array, we will be inserting the nodes. So I is the position where it has to be inserted. Obviously, it has to be, the item has to be, that is the last position has to be inserted. Then after insertion, after we add at the end position, we have to use and traverse till the root node. To do that, so that we have satisfied the structural property. To do that, we use a while loop I greater than 1. Because when I becomes less than 1, that means we reach the root. And A of I by 2 is less than the item. That is, the parent is less than the element which we are inserting. Then move to its parent. Its parent will be I by 2. That is why we have I by 2. And make I as I by 2. So A of I by 2, it's nothing but we are trying to go to the parent node, replace the parent node with I by 2. That is, the child is replaced with the parent. And then I is divided by I by 2, so that we go a level up. We move a level up. So if we look at the tree, the heap here, if this is I, if 90 is I, this will be I by 2. The second level node 80 will be I by 2. Its uh, last level will be I by 4. So so parent and child, if parent is I, child will be, sorry. If the child is I, parent will be on the I by second index. If its parent will be at I by fourth index. So that is why we have to move each level by level. It's looking at its parent. And remember, when we are dividing I by 2, it's floor division. You will suppose if there are 7 elements and seventh position, for example, let us go back. This is for 90 is node 1, 1, 2, 3, 4, 5, 6, 7. So node 70 at the seventh position. So when I divide 7 by 2, what will I get? 3.5. But we don't have floor division values for indices. So we don't have floating point for indices. So we use floor. That is, instead of 3.5, only 3 is considered. That is the nearest integer. 3 is considered. So if 70 is at index 7, 70 by 2 is 3, and which gives its parent. So if you can see, node 90 is 1, node 45 is 2, node 80 is 3. So 70 is a 7, 7 by 2 is 3, so it gives the parent. If 50 is their node, node 50 is at 6th position, 6 by 2 is 3, so again it gives 80 as its parent. So here if you see, we have 50 and 70. 50 is at index 6, 70 is at index 7. So both when we divide gives 3 index 3, which is nothing but index of its parent, that is node 80. So that is what we are doing here and comparing with each and assigning. That is how insert is performed. Now adjust is nothing but the same problem, same thing over here. What we try to do, we look at delete, then we'll come back to adjust. And delete max, actually, delete max is nothing, as we have insertion. The same way we have deletion also. But remember, as in binary tree, binary search trees, you can delete any node, root node, any leaf node, any internal node you can delete. But in heap, deletion only happens at the root. On every time when when a deletion is performed, it is the root node which gets deleted. So the algorithm for deletion is nothing but when this 0, that is there are no elements, then he is empty, you cannot delete. Otherwise, remove a of 1. Always, I'm telling you, when deletion happens, always the root node is removed, deleted. When root node is deleted, then the last node is replaced with the root node. So root node is deleted, the last node is replaced with the root node, and then adjust is called. Let us first look at the practical, a way of deleting. We will look at an example of deleting. Now, let us look at this. Where is that? RNA. Let us look at this. Let us look at this heap. Is this a heap? Yes, 90 is there, 80, 35. Both are less, 40, 45, both are less than 80. Now, when we perform deletion, node 90 will be deleted. Node 90 will be deleted. Every time the root node is deleted. Node 90 will be deleted. Once node 90 is deleted, this node, this left subtree and this right subtree will be two different trees then. So what happens is, when node 90 is deleted, the last element from the heap, which is the last element? Node 90 is 1, 2, 3, 4, 5. Fifth element, which is 45. Last element is replaced with the root. So this node goes, this it's replaced with the root. So 45 becomes becomes the root node, and there is no what do we call, where is that marker? So 45 is replaced here. So this becomes 45. This instead of 90, this becomes 45. 45 is deleted. Then when this becomes 45, so always remember that the last element will get replaced with the root node. Then this satisfies the structural property because root node is there. You have its two children. It's the node 80's child. It's a complete binary tree. Structural property satisfied. But relational property will be violated. So what we do is for relational property, we will check its children. Which children is greater? The left child or the right child? In this case, it is the left child. So left child is swapped, whichever is greater is swapped with the its parent. So here instead of 45, we have 80. And here we will have 45. Instead of 80, we will have 45. Is it satisfying? Yes. Here we have 80. This is 45 and 35, which are both are smaller than 80. Fine. This is 45. And here we have 40 as its child. So it's fine, satisfying the relational property. So ultimately, we get a tree which will have 80. And then 80 will have 45. 45. Its right child will be 35. And then 45 has its child 40. So this will be heap after performing the delete operation. And the element which is deleted is the 90. It's the root which is deleted. So every time in a heap when we delete it, the root which gets deleted. So remember that. Now let's come back to the algorithm of delete max. So last element is the first root node is deleted, which is at index 1. Last element is assigned at the root node. Then this satisfies the structural property. These two statements in line 8 and line 9 satisfy structural property. So now we have to satisfy the relational property. That is, we have moved 45 to 40 and the parent child. That is done using adjust. So adjust algorithm is there to, is there to adjust the element such that the relational property is satisfied. If you look at adjust is just opposite. For example, when we had parent, you have child. So child divided by 2 gives you the parent. And parent multiplied by 2 gives you the child. But in child, we can have a right or the left child. So that is what we are doing. There we had seen an insert, I equal to I by 2. But here we are using a variable as j. And 2j we are using because always the parent and child will be at a different level. And when j is the parent, then child will be at 2i or 2i plus j. Anyway, so here we take the ith element, and if j is less than n, because now there in insert we checked I greater than 0 till I greater than, if I becomes less than I less than 1, if it's I greater than 1, if it becomes less than 1, what happens is you are crossing the root. So in insert you are moving from last level, last node till its root. In adjust, when we perform delete, you move from the root till the last element in the path, in the last element in that level. So item is taken, then j is less than n, you are saying, because nth gives you the last element. If j is less than n and a of j less than a of j plus 1, we are checking which two, who is greater, I mean the left child or the right child. So if left child is smaller, a of j is left child, j plus 1 is the right child. So if j is smaller than this, that means smaller than the right, that means we move j to the right side. So we do j equal to j plus 1. If we find at any point that it satisfies parent child, satisfies the relational property, that is parent is greater than child, we break. Doesn't do anything. Otherwise, we move to a down level. And down level is nothing but by 2. So J is the parent node, J by 2 will be the child node. And then this procedure repeats by loop till we go to the last element. So in insertion, we are inserting at we are inserting the node as the last element and moving till its root to satisfy relational property. In delete, since we are deleting the root node, last node is replaced with the root node, and then the last node is replaced with the root node, and then we traverse or when we move from the root node till the last node in the level on that path to check whether parent is greater than, to check whether parent is smaller than the child. If so, then we replace it or we swap it. So this is how HST works. Now there is something known as heap sort, and this heap sort works based on the heaps property. So if you look at the heap, now in this heap, this is a heap. Everyone knows this is a heap. Now when I perform delete operation, what happens? It's the root node which gets deleted. And root node in max heap always will be having highest element among, or that node will be the highest among all its children. So if you look at this, it's this node 90 which is the highest. Now when node 90 is removed, what will happen? Node 70 gets place of node 90, and then these two are property gets violated. So node 80 comes here, node 70 goes here. Next time when I delete, node 80 will be there, which is the next element, second element. So every time when delete is performed, it will be deleting the root node, and since the root node will be containing the highest element among the heap, so is every time when we perform delete operation is the highest element which gets removed. So we can use heaps for sorting purpose. Sorting is nothing but arranging elements in descending order. So when we sort, we perform we can use heaps to perform sorting. So what we try to do is, when there are n elements in the array A, all the elements are traversed using a for loop and inserted. Now insert, we know, creates a heap. So a max heap is created. Then n I equal to n to 1 step of minus 1, we start deleting. So this is a reverse for loop, decremented for loop. We start deleting. Delete max, will give you the maximum element, delete the root, gives the maximum. That maximum element, whatever is deleted, which is x, will be assigned to A of I. A of I starts from n, remember. So what we are doing, it's going reverse way from n. So first time when delete max is called, largest element is deleted when I is 1. When I is n. So A of n is the last element. So in that array itself, last element is the highest element which is stored. Next, again delete is performed, I becomes n minus 1. At second last position, second last element is stored. So delete max is called repeatedly for n number of times, so that every time a node which gets deleted will be the highest node among the elements remaining in the heap, and that is assigned to the array. So that is how we can make use of heap sort. Heaps, we can make use of heaps for sorting the set of elements. Then there is something known as an algorithm known as heapify. This heapify is nothing but again creating a heap itself, but insert was inserting each element by element and creating a heap. Heapify means we already have a tree, a binary tree. That binary tree, we convert that binary tree into a heap. That is known as heapify process. And obviously heapify also, you have to look at nodes and try to maintain whether it's a relational property or not. Obviously that tree has to be a a complete binary tree, so that it's satisfies the structure property. But for relational property, what you have to do is you have to again call adjust. And adjust is called on every time one half because uh, when we select left and right nodes, they will be adjusted. I mean simultaneously. If left is greater than right, and you're making right the left swap with its parent, then obviously half of the tree is done. So heapify we will call adjust method again to balance the relational properties so that the binary tree gets converted into heap. So heapify is nothing but converting a tree into a heap. So let us look at another example, the last example in this one. This is nothing but we have 100, 119, 118, 171, 121, 152, and 132. This is a complete binary tree, structural property satisfied, but relational property is not satisfied. That is why we will perform heapify. When we perform heapify, you can look at the stage 150, 118 is there. These two. So we are starting from the last n by 2. These two elements get swapped. That is 151, 118 get swapped. So at this place 118, 132, they both are smaller than 151. So at this stage it is completely the property is satisfied. Then here you can see at this stage for this part 171, 112 is there, 119 is there. So 119 gets swapped with 171 because 170 is greater than 112. So at this stage also it is satisfied. Now we have to move to a level up, that is n by 2. So this is this level up. At this level we will be looking at its parent 171, 151. 171 is greater than 151. So 100 is swapped with 171. But 100 comes here. But when 100 comes here, then 119 is over here, which is greater than 100. So again this 100 comes here and 119 goes there. So this is how the binary tree is complete binary tree can be converted into a heap using heapify method. This was all about the priority queues. Now there is another topic we will move on is the graph. This is also elementary data structure which you have already seen in your data structures. Now let us quickly go through what graphs are. We are not going to go into detail because rest of the other parts of graphs we will try to look in the third unit, fourth unit, I suppose, where we have breadth first and depth first search traversals. Now, this figure, if you look at this figure, if you observe this figure, what is happening is this figure is okay. If you look at this figure, what you can see is there are certain vertices or some nodes. And those nodes are connected through some lines. Formally, a graph is a set of vertices. You can call it as nodes also, but in terms of or in graphs terminology, nodes are known as vertices. So graph is a set of vertices. So in this case, we have set of vertices known as V. We have 4 vertices, 1, 2, 3, 4, and a set of edges, which is E. So a graph is represented using set of vertices V and set of edges E. Each edge contains a pair from one node, from one vertex to another vertex. So if you see this pair 1, 2, so there is an edge between vertex 1 to vertex 2, 1, 3. There is an edge between vertex 1 to vertex 3, 1, 4. some edge between vertex 1 to vertex 4. So all this within the set of V are known as edges, set of edges. So graph is represented using set of vertices and set of edges. Now, if you look at this graph, graphs may have the edges of the graph may have orientations. If the edge doesn't have an orientation, it is known as undirected graph. And the edges of the undirected graph are ordered. So there is an edge between 1 to 3, 1 to 2, 1 to 4. There is no direction, no orientation on that edge. So these edges are known as unordered edges. And a graph with unordered edges is known as undirected graph. Let us look at another scenario. Now, everyone will look at this and say that this is a tree. This tree can also be represented as a graph. So we will call it as a tree, but can be represented as a graph, which has a set of vertices V as 1, 2, 3, 4, 5, 6, 7, and set of edges. That is 1 to 2, there is an edge, so 1 to 2. 1 to 3, there is an edge. 2 to 4, there is an edge over here. 2 to 5, there is an edge. 3 to 6, there is an edge. 3 to 7, there is an edge. So this is also a graph, but usually it is called as a tree. Now, is this directed or undirected? It is undirected because there is no orientation for the edges, and edges are unordered. So this graph is basically a tree. Now, why we are calling this as a tree? We will there's something known as cycle, and we will look at that definition later in these slides. So, but this is called as a tree. Now, let us look at this graph. This graph, there's 3 vertices, 1 to 3, and their edges is 1 to 2, there is an edge. Now, at this case, you can see that in this example, what we find that the edges have some direction. There is an arrow to the edge. When edges has direction, that means edges has orientation. So this graph, or a graph which has orientation or edges which has orientation or direction, then those edges or the graph, the edges are known as ordered edges, and the graph itself is known as a directed graph. So in a directed graph, edges are ordered and there is an orientation or a direction to the edge. Oh, sorry. There. So, when there is a direction to the edge, what this means is there is an edge between 1 to 2, as well as there is an edge between 2 to 1. So the arrow of the edge represent the direction of the arrow represent from edge is going from which vertex to which vertex. So there is a from 1 to 2 there is a edge, from 2 to 1 there is an edge, and then from 2 to 3 there is an edge. So this is known as a directed graph where edges have orientation. The next thing. Now when this the graph on the left side, this is a directed graph because all edges has orientation. And if you observe, there is an edge from vertex 1 to vertex 1 itself. So this edge is known as self edge or self loop. This self edge and self loop we will not be using or considering. We don't consider. It's not permitted in design and analysis of algorithms because there are various algorithms which may not work if we have a self loop, and there is no point in having a self loop. So realistically, what we say is it's not legal to have a self loop. It's not permitted. There is a restriction. So we say there will not be any self loop. As well as if you look at the graph on the right side. In this graph, you can find that there are multiple occurrences of the edges. Though this is undirected graph, there's no direction, but there's multiple occurrences of the edges. Now, this multiple And remember, this is undirected graph. If it is directed and one edge is going from 2 to 4, another coming from 4 to 2, that is no problem. That's not a problem. But here there are multiple edges and the graph is undirected. So this multiple occurrence of edges from 2 to 4, or even here, the next one, that is 3 to 4, these edges, there are 3 edges from 3 to 4. There is no direction also. These are multiple occurrences of edges. This is also not permitted. This is known as multi-graph, and is not permitted, is not used in this course. So we don't consider graphs which have self loops and graphs which have multiple occurrences when the edges are undirected. So these two things are not permitted, so we will not be using it, and the textbook itself will not consider this. Now let us see another definition in graph terminology, which is known as a complete graph. Now let us look at this graph. We say that this graph is a complete graph. Now in simple sense, a complete graph is a graph in which each vertex is connected with an edge with all other vertices. So if you see vertex 1 is connected, all other vertices are vertex. If we take vertex 1, all other vertices apart from vertex 1 is vertex 2, vertex 3, vertex 4. So vertex 1 is also 2 is also connected with 1, 4 is also connected, 3 also. Same way with 3, vertex 1 is connected, 3 is connected, and 4 is connected. With 4, vertex 2 is connected, 1 is, and 3. So with 3, vertex 1 is connected, 2 is connected, 4 is connected. So if you pick a vertex in a graph, all other vertices apart from that vertex will be connected for every vertex, this is known as a complete graph. Now, mathematically, a graph which has n vertices, if a graph which has n vertices also has n into n minus 2 by 2, n into n minus 1 by 2 edges. A graph with n vertices having n into n minus 1 by 2 edges is known as a complete graph. This is how mathematically we represent graphs. Now there are 4 vertices here, so n is 4. So 4 multiplied by 4 minus 1 is 3. So 4 into 3 is 12. 12 by 2 is 6. You can find that this graph has 6 edges. So any graph with n vertices having n into n minus 1 by 2 edges is known as a complete graph. Then there's some topic known as subgraphs. Now this is a graph, the top one is a graph. Its subgraphs these are its subgraphs. So how will we define subgraph? A subgraph will have vertices as the subset of the original graph. For example, 1, 2, 3 is there. So here, set of vertices 1, 2, 3, 4. So 1, 2, 3 is a subset of 1, 2, 3, 4. Even here you can check same way. Even this is a subset, there's no problem. Then edges also will be a subset of the edges of this original graph. So subgraphs are nothing but a part of those graphs. So these are the 3 possible subgraphs. Well, you can have many more subgraphs. Let us take this. Even a single node, vertex 1. It's a subset of vertex 1 to 3. So it's a subgraph. We can have these 3 vertices connecting 1 to 2. It's a subgraph. Even this is a subgraph. Even this is a subgraph. So subgraph means it's a part of the graph, part of the vertices, part of the edges, sub-edges, sub-vertices. So these are some examples of subgraphs. Now let us look at some more few definitions over here. Now here what we have is, if we have an edge between vertex u to vertex v, some vertex u to vertex v, then we say that vertices u and v are adjacent. So in this case, in this left side, 1 and 2 is an edge, so 1 and 2 are vertices 1 and 2 are adjacent. 3 and 4 is an edge, 3 and 4 is an edge. So what is 3 and 4 are adjacent. Now what about this graph on the left side? 1 and 2 edge, 1 and 2 is an edge, so they are 1 and 2 are adjacent. 1 and 3, there is no edge between 1 and 3. 1 and 3 is not an edge. So note what is 1 and what is 3 are not adjacent vertices. So adjacent vertex means if U and V are is an edge, then what is U and V are adjacent vertices, or they both are adjacent. Then there is another definition known as path. Path is nothing but from vertex U to vertex P, if there is a sequence of vertices such that there is an edge between each pair. So for example, if you consider this graph on the left side, from vertex 1 to vertex 2, there is an edge. From vertex 2 to vertex 4, there is an edge. From vertex 4 to vertex 3, there is an edge. So there is a path between vertex 1 to 2, 2 to 4, 4 to 3. If you consider this graph on the right side, there is an edge between 1 to 2, and from 2 to 3, there is another edge. So there is a path between 1 to 2, 2 to 3. Though in this case, 1 to 3, there is direct edge, 1 and 3 are adjacent. But when we say path in this graph, 1 to 2, 2 to 4, 4 to 3 will be a path. In this case, there is no direct edge between, on the graph on the right side, direct edge between node 1 to node 3. But there is a path between node 1 to node 3, that is from node 1 to 2, from 2 to 3. So this is what is a path. Now, I told you we'll talk about cycles later. A path in which the first and the last vertex is the same is known as a cycle. So if you look at this case on the graph on the left side, 1 to 2, 2 to 3, 3 to 1. 1 to 2, 2 to 3, 3 to 1. There is a path between 1 to 2, 2 to 3, 3 to 1. So this forms a cycle. Now here in this case, we have a path between 1 to 2, 2 to 1, 1 to 2. This is directed graph, 1 to 2, 2 to 1. So this is a cycle. But in this case, there is no cycle between 1 to 3. Because you can go to 1 to 2, 2 to 3, but from 3 you cannot go again back to 1. So there is a no cycle between 1 to 2, 2 to 3 and 1. But though there is a cycle between 1 to 2. Now, the difference between graph and tree is that graph will have cycles. Graph can have cycles. May or may not. That is also a different issue. But usually graph has cycles. But tree will never have a cycle. Tree will never have a cycle. That's the difference between graphs and trees. Now, let us look at another topic or definition or term, connected graph. If we say graph is connected if and only if every pair of distinct vertices, remember, distinct vertices means different U and different V's. For every pair, there is a path from U to V. Now, if you consider this graph on the left side, how many vertices are there? There are 4 vertices, and from every vertex, you can reach every other vertex. That is, between different distinct pair of vertices, there is an edge. So actually, every pair of vertices, there is an edge. Let us consider the graph on the right side. Now here, don't get confused. Just a second. Here, don't get confused. These are not 3 graphs. These 2 things, these 2 subgraphs, no, these ones, these 2 are single graph. There are no different graphs. That is why nodes are numbered from 1, 2, 3, 4, 5, 6, 7, 8. So these 2 are singles graph. So the set of vertices, there are 8 vertices in this graph. Now this graph is not a connected graph because you may have 1 to 3, there is an edge, or there might be a path from 1 to 4 using 1 to 4, but there is no path from 1 to 5, no path from 2 to 8. You can't reach it. So between there is, for every pair there is no, we do not have paths. So this is known as, this is not a connected graph. This graph is not a connected graph. This, because there is no, at least there should have been an edge between 2 to 6 or 6 to 1 or any other. These are two disjoint graphs, what we call it. These are not connected graphs. Now, connected components. We talked about connected graphs. Now let us talk about connected components. Now, suppose if there is an edge between 2 to 6, then this graph is a connected graph. But there is no edge between 2 to 6. So these two are disjoint subgraphs, actually. This becomes one connected component, and this becomes another connected component. So what we say is, this graph, the entire graph, has two connected components. Let us look at another scenario, or let us look at another graph. Here we have A, B, C and D, E, F and G, and between C and E there is an edge. Now, connected components also as connected subgraphs is known as connected component. Here, if this edge in red is removed, then this becomes one connected component, this becomes another connected component. Now, there is an edge known as article. There is a edge which connects between, in a graph, there is an edge which connects between two vertices, and removing that vertex will result in two connected in different connected components. Might be different connected, not only two connected components. Then that vertex is known as an articulation point. So in this case, if I remove node C, then there will be two connected components. So node C is an articulation point. In the same way, suppose if I remove node E. Node E is an articulation point, because removing node E we will have two connected components. So articulation point is nothing but a vertex whose removal will result in connected components. If I remove node D, am I getting connected components? No. So node D is not an articulation point. Now, by connected components. Now what happens is, last example, we had edge between C to E. If we remove edge C to E, we get two different connected components. But now here what we are having? We have an edge between C to E as well as from A to E. So if I remove this edge, the graph doesn't, we don't have connected components, because there is still an edge between A to E, and from this edge we will be able to reach all the vertices on the left component or on the right component. As well as if we remove this A to E edge, we have an edge between C to E. So all the vertices are connected. So this is known as bi-connected components. That is, there are two edges, and two components are connected by those two edges. Removing of one edge, if there was only one edge, removing that edge will result in connected components. But in a bi-connected component, removing these two edges, removing any one edge will not result in connected components. So that is one. But edge between A to E and C to E are known as bi-connected components. Now, nothing. Okay. Now here, let us look at the topic of what we call of how to represent graphs. There are several ways of representing graphs. Actually, there are four different types, four different ways of representing graphs. But in this course, we talk about or concentrate on two ways. That is, one is the adjacency matrix, and the other one is the adjacency list. Adjacency matrix is nothing but an array of n by n. Sorry, it's a matrix n by n matrix, not an array. Sorry, it's an n by n matrix, where n is the number of nodes or vertices. In this case, we have four vertices, so we will have 4 by 4 matrix, and each row and column, the intersection of row and column will give us an edge between them. So if you look at this one, you have node 1 to 2. So in a row, wherever we have node 1, the cell of node 1 and column 2, we are having 1, which means there is an edge. Wherever we have 0, that means there is no edges. All the diagonal elements of this matrix has zeros because diagonal elements represent self loops, and we have already said that we will not be considering self loops or self edges. So we say all the diagonal elements are 0. So if there is an edge between 1 to 4, then in row 1 and 4th column we have 1. This is for undirected graph. So when we say there is an edge between 1 to 4, there should also be an edge between 4 to 1. So that is why first row, 4th column is 1. 4th row, 1st column is also 1. So this is undirected graph. That is why we have to show that, or we have to represent that when there is an edge between U to V, there is also an edge between V to U. In the other case is that this is unweighted graph. That is, the edge doesn't have weights. That is why to represent edge we are using 1. So wherever you find 1, that means there is an edge. But suppose if there is a weighted edge, this is a representation of another graph. Suppose if there is an edge, edge has weight. For example, this from 1 to 2, the weight is 2. From 2 to 1, assume that the weight is 4. So what we do is 1 to 2, this is a directed graph. 1 to 2, so row 1, second column, instead of 1, we will have the value as 2. And then 2 to 1, so second row, first column, 2 to 1. Instead of 1, we will have 4 as the value. We will have 4 as the value if the edges are weighted edges. Then this is the same represented. This whole thing is one graph. They are not two different graphs. Period. Class चल रही. Just a minute. Okay, then now this one. Let us take this example. Now this one is not a. These are not two different graphs. These are disjoint graphs. This is a single graph. There's two components. So what we have is, we have, since there are 8 vertices here, we have 8 rows and 8 columns. Now the next thing is the different way of representing is adjacency list. In adjacency list, what we do is we don't make the entire what do you call array, or as adjacency matrices needs a lot of what do we call space in terms of representation. So to reduce the space and all, we make use of adjacency list. So adjacency list, we make a head node. There is a list. We make one list as head node. For every vertex, we make that as a list head. Then from node 1, who has an edge? Node 4 has an edge. So we will create a node and assign 4 to that element. Then node 1 also has an edge to node 2. So from node, this is a linked list actually. This is a linked list actually, which contains all the vertices which are part of adjacent to vertex 1. So node 4 is there, node 2, node 3. So there's a list. For node 2, node 3, node 4, node 1. So this is a list. So each node will have its list. Same way, look at this. Node 1, 2. So node 1 is there. Node 1, 2, 3. Node 1 is there. Node 1 has is adjacent to node 2. So there is only one edge in this vertex in this list. Node 2. Node 2 has an edge to node 3 as well as node 1. So two different nodes. So this is basically a list for each node, and each list contains adjacent nodes. So that is what is all about adjacency list and how graphs are done. Now in the next class, we will take up the topic of sets and unions, which is most important. We will wind up this class now because the college is getting closed. Actually, we are in college. Just a minute.